All right, the final part of this chapter is chi-square analysis. So chi-square analysis evaluates as a way to account for the fact that chance has an effect on genetic data. And so your question that you're asking is the experimental results that I see, do they differ from the expected ratio based upon chance, or do they differ from the expected ratio because something different is going on? And so what is the motivation for wanting to ask this question? So I have asserted to you that Mendel performed all of these different crosses, and when he looked at the F2s of all these monohybrid crosses, he saw a 3-to-1 ratio. So, he wrote out, he looked at, thousands of F2 animals, and he found that approximately this matched a 3-to-1 ratio, but not exactly. So this was 2.96 to 1, this was 3.01 to 1, this was 2.82 to 1, 2.84, etc. And so we might want to ask the question, are these actually 3-to-1 ratios, or did Mendel get it, off, and maybe there's something else going on that we need to account for? And so how do you actually ask that question? We know that there is room for chance to make things not exact. So if I rolled, 2 dice together, I would expect the number 7 to come up the most often. But, if you only do this a couple times, chance is very important, and you might roll a 6, a 9, an 8, and you might not see a 7 for a long time. And that's perfectly reasonable. And so the chi-squared test is a way to ask this question in a statistical manner. And so the question we are going to ask is, are these ratios actually 3-to-1, or are they different? And so we can do this, for example, for both monohybrid crosses or dihybrid crosses. And we can really ask, are these things sorting independently from each other? So for these, we have our null hypothesis. And so our null hypothesis is that the ratio is 3-to-1, and that the reason that we see differences from this 3-to-1 ratio is just due to chance. And so the chi-square test allows us to ask, how good does our data fit the null hypothesis? So what we're going to do is we're going to analyze the difference between the observed versus the expected values. So how do we do that? So let's say we do a monohybrid cross, and we cross, big R with little r. And then in the F2 generation, we measure 740 that have either big R, or big R, little r. Again, we're just measuring the phenotype, so we don't really know. And then we measure 260 little r. So 740 are round, 260 are wrinkled. And so that's approximately 3-to-1, but it's not exactly 3-to-1. So we've measured 1,000 offspring, and we've gotten a ratio. So to do this chi-squared analysis, what we need to do is we need to actually calculate the expected number that we thought we would see. And so the expected number would be 3-to-1. So we think that we should see 3-to-1. And so for those 1,000 offspring, what we expected to see was 750 be round and 250 be wrinkled. So that would result in a 3-to-1 ratio. So here we're just filling out this table right here. So our expected ratio is 3/4 to 1/4, so 3-to-1. What we observed was 740 to 260, and what we expected was 750 and 250. So now we calculate this deviation, and so the deviation is simply subtracting these two numbers. So the observed minus the expected. So we get -10 and +10. The deviation, then we square that. So -10 squared is 100, and then we get 100 for that. We calculate this d² over e, And so we take the 100 divided by the expected, and we get 0.13. 250, so we get 100 divided by 250, and we get 0.4. And so we add all of this up in order to calculate a chi-squared value of 0.53. So the first thing that we need to do is calculate the chi-squared value. We can also do this, for example, with dihybrid crosses. So our expected value of dihybrid crosses is 9 to 3 to 3 to 1. So if we observed 108 individuals and we categorized their phenotype, we would have, a distribution that might look like this. So 587 had dominant of both, 197 had one recessive, one dominant, etc., etc. The expected would just be taking 1008 by 9/16, etc., just like we did up here. So again, we can calculate the deviation by subtracting these numbers. We can square that, and then we can calculate the d squared over e value. And then we can sum these all together to get a chi-squared value right here. So in both of these cases, we calculated this chi-squared value by following this procedure. So now what we want to do is we want to translate this chi-squared value into a p-value. And so is it very unlikely to get this distribution? So basically what this p-value is to say, if our expected number is this, how unlikely was it to get this? And so we got to translate this chi-squared value into a probability. So if it was very unlikely to get this data, then we would say, okay, this does not seem like it's actually by chance. And so unfortunately, we also have to calculate the degrees of freedom in order to translate this properly into a number. And so the degrees of freedom is simply the number of different categories into which the data points may fall, and then we have to subtract 1. So for the first case, for the monohybrid cross, there was 2 different categories. It could be either round or wrinkled. And so the degrees of freedom is simply 1. And then for the dihybrid cross, it was 9 to 3 to 3 to 1. So there was 4 different categories that it could fall into. So the degrees of freedom is simply 3. And so once we have that, we can use a chi-squared table that allows us to translate this value from a chi-squared value to a probability. And so this is a table. So if the degrees of freedom is 1, these are kind of cutoff points where the chi-squared value, if it's greater than a certain value, means that we would say it does not match the expectations. So, one of the things we can do, this line allows us to actually translate it. So how do we do this? So for the first case, we had a value of 0.53, and there was 1 degree of freedom. So if we mark this chi-squared value right here, we go up to the degree of freedom line of 1. So this is degree of freedom 1. And then we simply just follow this over here to get a p-value. So the p-value is approximately 0.48. In the second case, we had a value of 4.16 with 3 degrees of freedom. So 4.16 is approximately here. And then the degrees of freedom line that we're looking for is this one right here, right? So we would go up until we reach that line, and then it would be somewhere around 0.2 would be the probability. And let's just compare, this was 0.26, so my ability to draw straight lines was not perfect, but I got it approximately right. So for us to say that the data is inconsistent with our expected value, we need to have a probability of 0.05 or below. So these are simply the cutoff lines. So if for a monohybrid cross, the chi-squared value would have to be greater than 3.84. For a dihybrid cross, since there's 3 degrees of freedom, it would have to be greater than 7.82. For a trihybrid cross, you'd have to calculate, for example, how many different categories are there, how many different phenotypes, and then you would use the degrees of freedom for that, for example. So hopefully that all makes sense. So most of this chapter should be review, and hopefully you've just expanded a bit upon how to do this in preparation for the following chapters.